So what we wanted to take a look is to present that method and some of our results. So as you probably know from now, Whisper is a large language audio models, which is multilingual, and it's been used with several languages at the same time. And we've investigated 3 languages, English, which has the most training data, French, which is number 5 in terms of the training size, and Persian, which only has 24 hours of speech for the training data for the transcription task, because that's the task that we analyze. We looked at the internal representation of Whisper using the C++ implementation developed by Jarganov, and our colleague Jean-Baptiste Yunès did the coding and is now available from Jarganov's initial GitHub. I'll explain the principle, but we can extract the probability for the predictions. Here in this paper, we only analyze the probability assigned to the first prediction, the one that is retained in the transcription. And we try to compare how the analysis based on the transcription of each subtoken, not of the word as such. As you know, the words are split into subtokens, so we're not looking at word error rate. If anything, we're looking at subtoken error rate. And this allows us to show that there was some kind of architectural bias, and as predictably from the size of the training data, there were accuracy in the training data. So we used 1 hour of French from the Corpus du Français Parlé Parisien, Persian French. The data is available online, and it's contemporary conversation. We have a similar corpus from the Ateros corpus that was designed to analyze conversation. Because there were so many errors with Persians, we took a very limited set of recordings. We had 2 female Taiwanese speakers reading aloud in read speech 120 sentences that included a specific type of dislocation. I'll explain how we've extracted the timestamps and the subtoken probability from Whisper. We've used the pipeline to produce the text grids for Pratt potential analysis, and we analyzed how the predictions were correct or not correct, looking at on the individual basis of the predictions. So here's the pipeline. That's the sound signal from Whisper. We can extract the SRT, namely timestamps, and with which we can do text grids with Pratt. For another paper, we've looked at the effect of speech rates with these text grids. With Whisper, we extract the subtoken sequences and the corresponding subtoken probabilities. These are the different types of data sets that we worked on. So there's a strong discrepancy between the number of hours used for the different tasks. We computed that out of the complete total of hours of audio for Whisper, if we take out everything that's taken for other languages than English, this means that for English, we've got more than 500,000 hours of speech to be compared with Persian, only 24 hours. We used a method that has been potentially used for the semantic analysis of large language model, the calibration curve method that plots the probability as the x-axis and the success of the prediction on the y-axis. And we can see the result is here. The perfect prediction, the perfect model would be the x equals y line. And you can see that the models slightly remain in a way overconfident in their predictions. And we can see that for Persian, we have the most striking features and differences. This is also true for the different languages, the assumption being the model is not perfectly calibrated for Persian because with a very low probability, according to the system, which could be equated to the confidence the system has in its prediction, you do have potentially proper predictions. So the second thing that we noticed is that for French, the more the word is split into subtokens, the more likely you have to observe errors. So the y-axis corresponds to the success rate, how many of the predictions were accurate, that's accuracy. And the x-axis corresponds to the number of subtokens. Because it's a multilingual system, the byte pair encoding is such that frequent word, especially English words, are usually representing only one subtoken. But for French, especially for female nouns, you do have more subtokens, and the more subtokens you have, the less precise is your transcription. We do observe some kind of a potential confounding factor. The nouns that were subtokened into 5 subtokens were also place names describing Paris. It's a recording about the streets of Paris and the places of Paris. So there might be a confounding factors between the transcriptions of named entities, which is an issue as reported in the Radford paper describing Whisper. We also try to see if the part of speech had an effect. We had the assumption that part of speech that were most frequent were likely to be more often than not well transcribed. This is partially validated with the case of prepositions having a perfect accuracy and conjunctions having a perfect accuracy. But because English, that's the data for English, as an alternation between strong and weak forms, we do have potential mismatch for the realization of weak vowels and full vowels, which may explain why the preposition to may have an issue and why the auxiliaries might be less well transcribed in our data. So how does Whisper probing for predictions present itself? When you extract the data from the C++ implementation, you have the special subtokens from Whisper. You have here, I'm come back on that point, on that problem, and come back in French is spelled into 2 subtokens. You have the probability assigned by Whisper to the subtoken, and you have timestamps which are not perfectly accurate. And with these data sets, we produce the analysis for the calibration analysis. And we also try to do reverse engineering. We try to understand the meaning of the Whisper's dictionary of subtokens. Some of them are described in the documentation. They're the special tokens. BEG that you saw here stands for beginning, but TT is not documented. We wanted to know what it meant. We eventually try to observe that they correspond to temporal subtokens. So if we look at the value of these TT subtokens and the time elapsed between the BEG session, we can see that there is a certain form of regularity. And if we take a strict measure on the timestamp from every 30 seconds, you may know that Whisper has been trained for time spans of 30 seconds. The prediction is done. And you can see here that's this really linear model that says that basically the bigger your TT model, the longer from the beginning anchor point it represents. So these TT models actually are indices of time. We looked at the effect of the training size. So we took the log of the training for Persian. That's very small for the 24 hours. And this is the log for English and French. And we computed the expected calibration error. And you can see that there's a linear prediction. The more data you have, the less errors you're likely to have. That's reassuring in the terms of the system. Some limitations to our study. We did not look at the fine-tuned version of Persian. We only looked at 3 languages, so we may observe some specific issues related to Persian, and they are now the focus of our current work. And we, in a way, did an easier test for Persian because we used read speech, not spontaneous speech. Nevertheless, we hope to try to show the interest of these probing methods where we can try to analyze some of the performances of Whisper. That leads us to the analysis not only of word, but also the subtoken. We've tried to see that there's some kind of architectural bias of the subtokenization for French, but we want to continue this analysis of the effect on other languages. And as a side paper, we've also looked at the effect of the subtokenization and translation task, and it's not that clear. It's clearer for the transcription task than for the translation task. And we have a current paper where we examine the consequence of subtokenization for Persian. These are the key references. And feel free to email me as the contact person for this joint work if you have questions. And now it's question time.